So suppose I'm asked to prove that the sum of the first n even numbers is n times n plus 1. One way to look at that would be to consider, and again, the sum of the first even numbers, 2 plus 4 plus 6 plus 8 plus dot 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 plus n, which would be my 2i. Let's actually write that, so that's going to be 2n. One way to look at that would be to factor a 2 out of each of my terms. So then I would be looking at 2 times 1 plus 2 plus 3 plus 4. We recognized that was an arithmetic series, and my formula for the first n terms of an arithmetic would be the first term 1 plus the last term is n. So here's my first term of 1, last term of n, so t1 plus tn, times n all over 2, and if I have that 2 up front, those 2's will cancel, so indeed I get n times n plus 1. So that would be a proof, proving that formula is true by relying on the fact that I have already proved that the sum of the first n integers is n times n plus 1 over 2. So a clever way to do it, not a proof by induction though. So now let's look at it, proof by induction. So if I go ahead and look at the writing out the first several terms of the series, I want to show that that sum is the indicated formula n times n plus 1. Thinking back what we just did, if we had done that, we could simply divide both sides by 2 and be done. And relying on our sum of an arithmetic sequence, if I divide both sides by 2, I get 1 plus 2 plus 3 plus 4 dot dot dot. And we know that that's going to be n times n plus 1 over 2, so we also could have looked at proving using our previous arithmetic series formula to prove it very quickly in one arithmetic step here, dividing both sides by 2. But again, I want to do proof by induction. So proof by induction says I want to show true for I equals 1. So step 1 here is I want to show true for I equals 1. And then the second case, I want to say if true for some I equals k, then true for I equals k plus 1. So pretty easy to show that it's true for I equals 1. The sum of the, or my first term here in the series, and the sum of the first 1 terms will simply be 2. If I plug a 1 into the formula, 1 times 1 plus 1, 2 equals 2. Great, I've shown true for I equals 1. Check. 2. I need to assume true for I equals k. That is 2 plus 4 plus 6 plus out there 2, my 2k, or I equals k. I need to show that that equals k times, I'm assuming that this formula is going to be true for the first k terms. So out 2k, that sum is going to be k times k plus 1. I'm going to assume that that's true. I need to show true for the first k plus 1 terms. I need to show true that 2 plus 4 plus 6 plus 8 plus 2k plus 2k plus 1 equals, now the formula for k plus 1 is going to be replace the k with k plus 1, replace the k with k plus 1, so I'd have to show that it's equals k plus 1 times k plus 1 plus 1, or k plus 2. And again, my strategy is to say, well, if this statement is true, how can I get this statement to be true? And if I look at left sides, all I've done is added 2k plus 1 to the left side here. Well, if I add 2 times k plus 1 to both sides, if this statement is true, then the left side is true by immediate inspection, and I would just need to show that by adding 2 times k plus 1 to this, I wind up with k plus 1 times k plus 1 plus 1. So let's see if that's indeed true. And indeed it is. Go ahead and add to this side the plus the k plus first term, go ahead and add it to this side, plus 2k plus 1. And then I've got this left side equal to this left side, this right side equal to that right side. Show that this equals that. And I do that by noting that I can factor out a k plus 1, leaving me a k plus 2, and I can rewrite that k plus 2 as k plus 1, and that's what I wanted to show. So, let's look at this by induction, but I'm going to actually try and keep as much sigma notation intact as possible as I do it. So, again, the first step is pretty much unchanged. Show true for I equals 1. The sum of the first 1 terms, well, is 2. By formula, if I plug a 1 in for n, bang, the formula works for I equals 1. So now, rather than writing out the series in terms, I'm actually going to think about keeping that sigma notation intact. I want to assume that the formula is true for the sum of the first k terms. So leave, you're going to go from I equals 1 out to k. I'm not going to write that series out. I'm just going to say, hey, there it is in compact form. I'm going to assume that that equals k times k plus 1. If I want to show that it's true, I want to show true for the first k plus 1 terms, well, the sum of the first k plus 1 terms is going to go from 1 out to k plus 1. I need to show by formula then, replacing a k with k plus 1. So that would be k plus 1 times k plus 1 is k plus 2. If this is true, how can I get this to be true? And the same thing, I've got to recognize that these two left sides differ by 1 term. If I add the k plus first term to this left side, I get here, but I can't just add I can't just add something to one side of an equation. I've got to add it to the other side. So add the k plus first term to each side here, and then the left sides will match, and then I got to see if the right sides match up. So to do that, I say, let me add that k plus first term to both sides of what I'm assuming to be true. So if I add that k plus first term to both sides, I get k I equals 1 of 2I plus the k plus first term, which would be 2k, plus 2, because that's 2 times k plus 1. And then I can rewrite that. That is the sum of the first k plus 1 terms. But I've got to go ahead and also add that I've added the k plus first term to the left side. I've got to add it to the right side. So if I do that, I get k plus 1 plus 2k plus 2. And I've got to then look at that and see, does that simplify to give me this? Well, let's see. K plus 1 plus 2, 2k plus 2, and I get k squared plus k plus 2k plus 2. I get k squared plus 3k plus 2, and indeed that factors into k plus 1 times k plus 2. So I've shown that if I add the k plus first term to each side here, I get what I'm supposed to get, the sum of the first k plus 1 terms being, by formula, k plus 1 times k plus 2.